Good morning, and day one of the last unit I'll ever teach you guys in high school. So this is called matrix algebra. It's actually really fun and easy, and we can see later on in the unit why it comes helpful for us to solve systems of equations. And I'll show you how you can use the matrix algebra feature on the graphing calculator. So this is just an added bonus in case you do take more math and it's not calculus. It's more algebra. So definition of what a matrix is. This is not Keanu Reeves, by the way. The matrix, actually this has been around longer than him, but it's a rectangular array of terms. So you'll have like, it almost feels like, looks like a Lego piece, a box. So you'll have different sizes of matrices, and that's the plural. Matrix is singular, matrices for more than one. So the row and columns make a difference. So the rows go across, left to right, where columns go up and down, kind of like the columns of the Pantheon, or like the columns. I think they say the Colosseum has some. It was a mess though when I saw it a few years ago. In any case, you have numbers inside, positive, negative, could be fractions also. So it's just a big chunk of numbers of terms. How are matrices equal to one another? Two or more matrices are equal if they have the same dimension, so the same row and column size, and has the same elements all inside. You could have the zero matrix, kind of boring. This definitely looks like a Lego piece because everything inside the matrix is zero. And the negative matrix, if A represents a matrix, a block of numbers or terms, its negative would be denoted as a negative sign out in front of the matrix. So then you can distribute the negative sign to all the terms inside. Operations are pretty much the same as real numbers, with some exceptions, of course. We can add, subtract matrices. So if A and B are matrices, then A plus B is also a matrix. Here, the thing is, if you're going to add them together, they have to be the same size because you don't want a mismatch of elements, right? Kind of like when you try to divide by 0, I think the calculator says dimension mismatch, or when you're trying to do a linear regression. If you have more terms in L1 than L2, dimension mismatch. So when it comes time to adding matrices, you can add them together by commutativity is fine. Likewise, associativity is fine. If you add 0 to A and reverse it, you still get A. And if you add matrix A to its negative and switch it around, you still get 0. Half of A is not the same as A divided by 2 scalar. So we don't really talk about division, okay? There's no such thing as division. What we could do is we can, if you want to divide all the terms inside, you distribute a half. So some examples I put together here, as you can see, this is matrix A, which has 2 rows. So this is a 2, and it has how many columns? I see 3. Likewise, matrix B, I see 2 rows, and how many columns? I see 3. So they both have the same dimension. I can go ahead and proceed and add. So this new matrix A plus B, I would take 2 plus 1 is 3. 3 plus 0 is 3. 3 plus 9 is 12. That's row 1. Next row 2, 4 plus 2 is 6. 5 plus 3 is 8. Negative 1 plus 6 is 5. So there's your new matrix A plus B. Negative A, what that denotes is we're going to negate all the entries. So negative 2, negative 3 is row 1. Row 2 would be negative 4, negative 5, positive 1. If you want to triple matrix A, you multiply all the entries by 3. So 3 times 2 is 6, 3 times 3 is 9. So there completes row 1. 3 times 4 is 12, 3 times 5 is 15, and 3 times negative 1, negative 3 completes row 2. Now, you'll notice how I'm chunking up these numbers. You do have to close them up with these big, large bracket signs. It can't be straight line. You use a straight line, it actually is another symbol operation we study in this unit. So it's called determinants. So we don't want determinants, you want to make big brackets, okay? Half of A. So if we're going to take half of A, we're going to take half of all the numbers. Half of 2 is 1. Half of 3 halves is 1 1/2, or simply 3 halves. So I'll leave it as an improper fraction. Half of 4 is 2. Half of 5 is 5 halves. And half of -1, -1/2. And yes, you can do orders of operations. So 3A, we need matrix 2B. So double up all the entries, all the elements of 2 becomes 2, 0, 18. 2 times 2 is 4, 2 times 3 is 6, 2 times 6 is 12. So now we distribute the 3 to matrix 3A, 2 to B, 2B, and now we can add the 2. So there is a sense of orders of operations too in matrix algebra. So 6 plus 2 is 8, 9 plus 0 is 9, 9 plus 18, 27, 12 plus 4 is 16, 15 plus 6 is 21, and -3 plus 12 is 9. Any questions? Might want to write them down or maybe pause the video. All right. So after adding, subtracting, making sure I have the right size matrix to match the other matrix, let's multiply. Now multiply is a little different, okay? And that's why I want to make sure I have plenty of examples here for you to try and move along accordingly. When you multiply matrices, okay, so the row times the column of matrix 1, so there's your first matrix. And your second matrix, you'll notice, does not have the exact same dimension, but the rows is the same as the columns. That's important. If this number here does not match that number there, you cannot multiply those two matrices together. What happens, the resulting new matrix will be a new dimension, the m times the p. It's kind of like the law of syllogism or the chain rule. You know, if you remember from geometry when you were doing proofs, like if I were to tell you if 1 plus 1 equals 2, then let's say today is Wednesday, then if today is Wednesday, then, hey, it's payday, let's say. So what conclusion can you make from these two sentences? Well, you can combine the two and it becomes if 1 plus 1 equals 2, then today it's payday. So that same kind of concept applies here. But the multiplying is not the same as adding because the dimensions. So if you see here, we have a 2 rows by 2 columns. And we have 2 rows here by 3 columns. So our end result will be a 2 by 3 matrix. So how to get my answers? Alrighty. It's going to be kind of confusing, I know, me being away here from you guys, but I'll mark my rows yellow. And I'll mark my columns here of the second matrix pink, okay? What you're going to do, you're going to multiply 2 times 1. And then you're going to add that to 3 times -1, -3. The answer you get is -1. That will give you your first row, column 1 entry. So again, you're going to take this row and line it up with this column and multiply the terms together and do a simple PEMDAS. Same idea with the next one. You're going to take 2, this 2 times that -1, and you're going to add that to this 3 times that 0. Ooh, that's -2. So again, this row times that column. And the last entry, this 2 gets multiplied with that 2. And then I see here 3 times 3. So 4 plus 9, 13. Takes a little while getting used to. So again, row 1 gets multiplied to each of these columns to give you the new row 1 of new matrix. Then we do the same thing here. So negative 1 times 1. And then 4 times negative 1. We're going to add those two together, and we get negative 5. So this, row 2, column 1. And after a while, you'll notice I don't write all of these operations down, but being that you're so far away and you're learning this for the first time, I do end up writing a lot of, looks like chicken scratch here. So again, negative 1 times negative 1 is 1, plus 4 times 0 is 0, and 1 plus 0 is 1. And lastly, this row, negative 1 times 2 is negative 2, and then 4 times 3 is 12, and negative 2 plus 12 is 10. Now, down the road, I'll show you how you can use the calculator to help you with that. But just in case, in college, most likely you will not be able to use the graphing calculator. You can use it as a check. But in this case, you have to multiply, but you have to make sure the dimensions match. Let's do another example. Number 2, before I proceed, I'm going to find the measurements. So we have 2 rows, 3 columns. So this is a 2 by 3 matrix. I see I have 3 rows and 2 columns, 3 by 2. So what will the end result here be? Since the end matches the top, the end result will be a 2 by 2 matrix. So we'll have entries here, here, there, there. Okay, so let's try. 1 times 1 is 1. Negative 1 times 5 is negative 5. And 1 times negative 1 is negative 1. So I get here negative 4, negative 5. And then I do the same thing. 1 times negative 1 is negative 1. Negative 1 times 2 is 2. Negative 1 times 3 is 3. So 1 plus 3, 4. Row 2 now. 2 times 1 is 2. 3 times 5 is 15. Uh-oh, I think my eyes just wandered. 1 times 1 is, yeah, I did. I was getting, I guess I can finish it off. 2 times 2, no, I was right. 2 times 1 is 2. 3 times 5 is 15. Negative 1 times negative 1 is 1. So I'll get 18. And last one, 2 times negative 1 is negative 2. 3 times 2 is 6. Negative 1 times 3 is negative 3. So I'll get your 1. Okay. Same thing here. We have 2 by 3, 3 by 2. So our end result will lead us to a 2 by 2 matrix. So again, 1 times 2, 2. 3 times 1 is 3. 1 times negative 1 is negative 1. We get here 5. 1 times 1 is 1. 3 times 3 is 9. Ooh, anything times 0, 0. So we'll get here 10. And the next, row 2. 2 times 2 is 4. 0 times 1, yay, 0. 4 times negative 1 is negative 4, so we get 0. And 2 times 1 is 2. 0 times 3 is 0. 4 times 0 is 0, so we get 2. So just make sure you get the hang of it. Go ahead, try number 4. So if you did it correctly, you would get something like this. Here we have a 3 by 2 matrix, and we have a 2 by 3. So the end result should have been a 3 by 3 matrix. So again, we take 2 times the 1 is 2. 1 times the 2, and that's how I got 4. 2 times 3 is 6 plus 0 is 6. 2 times 1 is 2. 1 times 4 is 4. That's how I got the next 6. So row 1 should have been 4, 6, 6. Then I took 1 times 1 is 1. 3 times 2 is 6. 1 times 6, that should not be a 5. That should be a 7. And then 1 times 3 is 3, because the 3 times 0 is 0. 1 times 1 is 1. 3 times 4 is 12, 13. And then negative 1 times, oh, I love the zeros. The more zeros, the easier matrix algebra actually is. So you get here, negative 1, negative 3, negative 1. So a couple things to keep in mind with matrix multiplication. Some things to keep in mind is they're not commutative. You can still multiply. We have something called the identity matrix. So it's not, when you multiply 1 to 3, you still get 3. When you multiply 1 to negative 2, you still get negative 2. The identity matrix, it has a diagonal of 1s, lots of zeros. If you multiply that matrix with another 3 by 3 matrix, it'll come back to you. So you can multiply an identity matrix to a matrix, get the matrix back. But the thing to keep in mind, you can't switch orders. Like for example, when we did that 2 by 2, let me do something simple. So here's a 2 by 2, and we're multiplying that by a 2 by 3. So 1, 0, 1, 0, 1, 1. Right, we can multiply because the end matches the beginning. But if you switch, do you think you can multiply 3, oh, wait, a 2 by 3 to a 2 by 2? No. So multiplication is not commutative when it comes to matrix algebra. So take a moment, watch the video, because this is something relatively new. You might have to watch the video a couple of times just to get the hang of this. I will send some work along, but probably the first day I'm just going to give you time to watch the video because it's something that no one here really has ever seen before. Thanks and have a great day.